Swayam Prabha. Digital India. Educated India.
Now, the charge across C1 is not negative, it just goes from the definition of voltages. Okay. So, there is no meaning to saying charge across C1 is negative. If you have a capacitor C with a voltage V with this polarity, the charge on this plate is C times V plus C times V, the charge on this other plate is minus C times V. Okay. So, that is what happens in any capacitor. Here, I have a capacitor C1 with a voltage VC1 defined in this polarity. So, the charge on this plate will be plus C1 times VC1 of 0 plus, and charge on this right side plate will be minus C1 times VC1 of 0 plus. Okay. Similarly, here the charge on this plate will be minus C VC of 0 plus. Okay. Any other questions? Okay. Now, I will not discuss circuits with inductors in great detail, but let me outline briefly what happens. Okay. And you can compare that to this RC circuit. Okay. And in both cases, I will take Vs jumping from 0 to Vp. Now, the current through this clearly is VR divided by R, and the same current flows through the inductor, and the voltage across the inductor is L times DIL by dt, where IL is the inductor current, and Vs, the applied voltage, is the sum of VL and VR. Okay. So, L times DIL by dt, which is L times dVR by dt times 1 by R. Okay, this is equal to L dIL by dt plus VR equals Vs. Okay. So, L by R times dVR by dt plus VR equals Vs, and in this case I will not derive it again, but we had done it earlier. RC dVc by dt plus Vc equals Vs. Okay. So, now in the RC case this was the time constant, in the LR case this turns out to be the time constant. Okay. I said earlier that a first order RC circuit, if you null the sources, will always be reduced to a single capacitor and a single resistor across each other. Okay. Single capacitor and resistor in parallel. Similarly, a first order RL circuit will always reduce to a single inductor and a single resistor in parallel. Okay. This always happens, and once you do that, the time constant will be equal to L by R, where L is that single inductor and R is that single resistor. Now, in the circuit there can be more than one inductor, right. What I mean is, I could have something like this. But when I null the source, what I have is that, and you can see that this L1 and L2 appear in series, and this is equivalent to L1 plus L2 and R in parallel. So, what will be the time constant of this circuit? The time constant is the inductance by resistance, and it is equal to L1 plus L2 divided by R. I think somebody answered saying L1 plus L2 times R, it should be divided by R. Okay. And because the differential equation looks the same for RC and RL circuits, the solution also looks the same. Let me rewrite it here. First order RL circuit, in this case if we want to find a voltage Vx as a function of time for t greater than 0, and I am assuming that there is a step input at t equal to 0. Okay. Vx of t will be Vx of 0 plus, sorry, Vx of infinity plus Vx of 0 plus minus Vx of infinity times exponential minus t by tau. So, you have to find Vx of infinity. For this, you short circuit all inductors. This is analogous to open circuiting all capacitors. This is because when all the quantities have reached steady state, which is a constant, okay, we know that the voltage across an inductor is the time derivative of the current through the inductor times the inductance. If IL is a constant, okay, VL has to be 0, and that means that you replace the inductor by a short circuit at t equal to infinity. Vx of 0 plus, what did we do? We short circuited all the capacitors to find the quantity just after the jump. So, in this case we open circuit all inductors, and finally the time constant tau is given by L by R, where L is the total inductance you see. It could be a combination of more than one in the null circuit, and R is the total resistance. Again, it could be the equivalent resistance of some complicated circuit. Across L. Okay. So, the algorithm is exactly the same, except that the time constant is of the form L by R. Okay. Hopefully, with this information you will be able to solve for step response in any RL circuit as well. Okay. Any questions about this? Any questions about the way to find step responses in an RC or RL circuit? Now, just like when we had loops of voltage sources and capacitors, if we have current sources and inductors in parallel, okay, current sources and inductors connected to the same two nodes, then you have to have a special case. You can think about that special case yourself. I am not going to discuss it here, okay, but it will be analogous to having loops of voltage sources and capacitors. There is a question, what does the total inductance in null circuit? I am not clear of what this question means, but for instance, in this case there are two inductors, but they appear in series in the null circuit. So, obviously, the total inductance is the sum of inductances. Now, if we are talking about a first order circuit, when you null the source, you should have a single inductor, okay, There may be separate inductors in this, but when you null it, you should be able to combine many of them into a single one. Okay. So, that is always the case in a first order circuit. If this is not possible, it is not a first order circuit. Everything we discussed so far applies only to first order circuits. Okay. Then we can go to, so far we have considered circuits that have a resistor and a capacitor or a resistor and an inductor. We have not considered cases where we have both resistor and capacitor and inductor. Okay, that is, we have capacitors and inductors in the same circuit. So, now we will consider that, and they will be known as second order circuits because they will lead to second order differential equations. So, first let me take a case where I have a voltage source Vs and this is applied to a series combination of R, L and C. Okay. And let me write everything with this capacitor voltage Vc as the variable. Okay. So, if the capacitor voltage Vc is the variable, we know that all these three components are series. So, there is a certain current that is flowing through the loop. What will be I of t in terms of the capacitor voltage Vc? Please give me the answer. What is I of t in terms of the capacitor voltage Vc? I of t would be C dVc by dt. Okay, because this I is nothing but the current flowing through the capacitor as well. So, it is C times dVc by dt. The voltage across the resistor VR is I times R, and that is RC dVc by dt, and the voltage across the inductor VL is L times di by dt, which is LC times the second derivative of Vc. Okay. So, we can form this differential equation Vs, or let me put Vs on the right hand side. We know that the voltage across the resistor plus voltage across the inductor plus voltage across the capacitor equals Vs. So, LC second derivative of Vc plus Rc first derivative of Vc plus Vc equals Vs. Okay. So, this circuit with a series RLC obeys a second order differential equation that is given by this. Now, in general, if you arrange the RLC in a slightly different way, it will also obey a second order differential equation. Okay. Now, we can of course solve this and find what the solution is. We do not have time to go through detailed derivations of the solutions of this. So, I am just going to give you the solutions in certain particular cases. Okay. So, before we go there, let me do it for a slightly different circuit. Or let me have R, L and C arranged slightly differently. Okay. And let me take the inductor current as the variable, okay, or rather maybe just like before I will take Vc as the variable. So, in this circuit I know that there is certain IL and certain IC, and this current equals IL plus IC. Okay. IC is nothing but C times dVc by dt, and also you see that the voltage Vc here is across the inductor as well. Okay. So, the voltage Vc is related to the inductor current by L times dIL by dt, okay, or IL would be 1 over L integral Vc dt, that is because the capacitor and inductor are in parallel. And finally, this current IR equals IL plus IC, which is equal to 1 over L integral Vc dt plus C dVc by dt. Also, we know that the current through the resistor is the voltage across the resistor divided by R. So, VR equals Vs minus Vc divided by R. Okay. Sorry, not VR, IR equals Vs minus Vc divided by R, or Vs minus Vc divided by R equals this whole thing 1 over L integral Vc dt plus C times dVc by dt. Now, this has integral and differentials in the same equation. We would like to have only a differential equation where everything is expressed as time derivatives. Okay. So, what I will do is I will differentiate the entire expression once more. So, I will end up getting, I will also move R to the other side, that is this R can be moved here. So, if I differentiate everything, I will get R by L times Vc, because the derivative and the integral cancel, plus this is Rc RC second derivative of Vc. So, if I rearrange this, I will get RC R by L Vc equals dVs dt. The reason I did this is to put the source on the right hand side and the unknown Vc on the left hand side. And I will rearrange this further. I will multiply the whole thing by L by R, and I will get LC this plus L by R that one plus Vc equals L by R dVs by dt. Okay. So, I am going to just derive the equations. The whole idea was to show that they will be in the similar form, okay, for both the circuits. So, let me put these side by side. So, this is the differential equation governing the circuit, and if I take the other circuit, I will have this other differential equation. Okay. The main point I wanted to make here is that the two are similar to each other. Okay. Mainly, especially the left hand side, it is of the same form. Okay. You get a second order differential equation. The coefficients are different. Okay. So, that means that the exact properties will be different, but both of them will give you second order differential equation. Now, it turns out that this is also true if you find some other arrangement of R, L and C, okay, and also you have current sources in the circuit and so on. So, what we will do in the next lecture is to get an idea of what the response of this circuit looks like. Okay. So, we will stop here today. In the next lecture, we will take up the second order circuits. If you have any questions, I will be happy to answer them now. Okay. If there are no questions, we will close here. I will see you on Thursday.